Combustion. In order to understand how a furnace works and how we are able to achieve proper combustion, we need to first understand exactly what combustion is. So what is combustion? Combustion is a chemical process of rapid oxidation in which fuel and oxygen produce heat and light. Combustion fuels, most commonly used in your heating applications, are natural gas, liquefied petroleum or LP, and oil. And there are three basic elements that are necessary for combustion to actually occur. We need to first have a fuel source. We need to have an ignition source or our form of heat. And we also need oxygen to help support combustion. And if we think about that, we put that into what is called a combustion triangle. You need to have all three of those elements in order for combustion to actually occur. However, each one of those elements need to be in their proper proportion in order for this to also occur. So, heat. Heat is required to initiate the reaction, and as the fuel and oxygen are combined, we are now able to give off heat and light energy. The following chemical formula shows the products of stoichiometric combustion. We have methane plus oxygen equals carbon dioxide plus water plus energy. So what is that saying to us? That is a combustion reaction. It is saying that we need to have a gas and an oxygen in order to create carbon dioxide and water. We also heard the name stoichiometric combustion. What the heck is stoichiometric combustion? It is perfect combustion. Okay, so in order for that to occur, the burning of a fuel occurs with the exact amount of oxygen needed to change that carbon and hydrogen molecules into water and carbon dioxide. Stoichiometric combustion, or better terms, perfect combustion, is never practical out in the real world. That type of combustion is really achieved when you are dealing with lab work, scientific experiments, stuff like that, where we are able to actually achieve and control all three of those elements. Complete combustion occurs when your fuel is burned in the presence of excess oxygen to produce water and carbon dioxide. But nevertheless, you must understand the perfect combustion formula in order to analyze how a piece of equipment is actually functioning. Okay, in perfect combustion, that formula, the ratio of oxygen and fuel is 2 to 1. And that is the only product of combustion are carbon dioxide, water, and energy. In regards to the heat, that concentration of heat is needed to start the chemical process of combustion. We got to have some sort of heat source in order for this to even further escalate into an actual burning. The heat required to initiate combustion is called the ignition temperature. Every one of our gases that we deal with in the HVAC industry has an ignition temperature. That ignition temperature is usually provided by either a pilot light or some sort of heated surface, such as a hot surface igniter. Okay, so the ignition temperature of natural gas is anywhere between 1100 and 1200 degrees. The ignition temperature for LP is anywhere between 920 and 1020 degrees. The reason why we have a difference in temperature is because of the difference in chemical composition between natural gas and LP. Remember, natural gas is lighter, has a specific gravity that is lighter than liquefied petroleum, or LP. Once combustion has occurred, that chemical energy in the fuel is released and converted to heat and light. And as long as that fuel and oxygen is present in that correct ratio, remember, all three of those have to be in that correct portion, no additional external input of heat is needed to sustain combustion. Combustion can only occur when the ratio of air to fuel is within an acceptable range. Okay, now the ideal ratio for oxygen of methane is 2 to 1. The ratio of air to fuel must be much higher, probably more about 10 to 1 if we're dealing with methane. That higher the ratio is because air is made up of 78% nitrogen and 21% oxygen. In a mixture of fuel and air, that fuel's flammability limits are now defined. And as the range of fuel concentrations within the fuel will burn within those ignition sources, as long as everything is necessarily present. So each one of our fuels does have a different upper and lower flammability limit. Let's take a look at methane here. Methane has 14% upper flammability and a lower flammability of about 5.3. But if you look at propane, propane has about 9.5 upper flammability and 2.4 lower flammability. So if we look at those two, you can see that in order for combustion to actually occur with natural gas, the fuel-air mixture must have a concentration of natural gas between 4 and 14%. The ideal concentration, though, for natural gas is anywhere between 8 and 10%. Okay, that concentration of less than 4%, it means it's running too lean. We're not getting enough air to support combustion. And if that was to happen, we are not burning off all those carbon molecules that are in methane. So therefore, we will probably be sooting up and not achieving enough temperature to properly heat a space. The concentration of more than 14% creates a mixture that is too rich, which means there is not enough oxygen available for all of the fuel to be present. The amount of air required for combustion is different for each fuel source. Again, go back to the way different gases are constructed, the different molecules. Primary air is the air that is mixed with the fuel prior to ignition. So there must be enough primary air available to support ignition. Any oxygen is consumed during the combustion process, it must be replaced. If we're using it, we have to have the ability to replace that air that is being used. And that is where that secondary air comes into play. Okay, secondary air is the air that is added to the flame after ignition to help support combustion. Secondary air surrounds the outermost area of the flame and maintains the combustion process. Primary and secondary air are commonly referred to as combustion air. You will hear that a lot in HVAC, combustion air, which is the air needed for complete combustion. So here is an example of what we mean by primary air. We have our gas source, we have our orifice, and here is our gas that's exiting our orifice. As the gas exits the orifice, we are now sucking in some primary air to help with that air-to-fuel mixture, which will travel up to the burners and then out. And as that burner ignites, we now have our secondary air. The secondary air is what helps support combustion and to make sure that all of the gas that we are burning is essentially burned off. All fuels contain hydrogen and carbon atoms at different amounts. Substances that contain only hydrogen and carbon are referred to as hydrocarbons. And since hydrogen burns more quickly and at a lower temperature than carbon, hydrogen is going to burn off first, using the oxygen from the air that it needs for complete combustion. Okay, hydrogen flames are a bluish color. And since the hydrogen in the fuel burns before the carbon, carbon atoms must travel to the outside edge of the flame to get oxygen from secondary air for complete combustion to occur. So carbon atoms burn more slowly and at a higher temperature than hydrogen. Remember, carbon is a little bit heavier. The carbon flame is going to produce a bright yellow type flame. Okay? Think about an oil-fired furnace, if you've ever worked on one of those. When an oil burner fires off, that flame is a little bit more of a yellowish-orange color. Natural gas is going to burn in a more bluish color. The flame color indicates when a proper amount of primary air is present in a gas furnace. If you have enough primary air and enough air surrounding that flame is going to be like a blue inner core with a light blue outer core. And that is going to indicate, this indicates that there are no unburned carbons. We want to see a nice bluish color flame coming out of our gas furnaces. Incomplete combustion is going to occur when the flame does not receive enough oxygen to finish the combustion process. And if there is not enough of that primary air, the tip of that flame is going to be like a yellowish color. The yellow tip is due to carbon particles that are not burned off. The outer edge of that flame, if it's burning like an orangey color, that is due to the burning of dust particles that were drawn in with the primary air. And it is not a sign of lack of primary air. It's okay to see a little bit of like an orange flicker occurring with your nice light blue flame. It's perfectly fine. But if you are seeing a yellowish, like a steady yellowish flame coming out of it, that means you've got incomplete combustion and that it needs to be fixed. So we have here is three little examples of incomplete combustion, which is number 1 here, and complete combustion, which is number 4. Anytime you see anything of 1, 2, or even 3, you are not burning completely. We want to see a nice dark core color with a nice light blue outer core. This is what we want to see when we're dealing with a natural gas furnace. If we don't have that, we are running the potential of running into carbon monoxide. Carbon monoxide is a byproduct of incomplete combustion. And it is a colorless, odorless, and highly toxic gas that can be fatal in a building, especially if the concentration gets too high. Anytime you are doing a service call or a maintenance on a gas-fired furnace, you should be inspecting the flame during operation to check for incomplete combustion. You want to physically see what that flame looks like. All heat exchangers should be inspected for cracks as well. Okay, because the heat exchanger is the only defining piece of equipment that is inside a furnace that divides between life and death. We need to be inspecting that to make sure that it is intact. A carbon monoxide detector, you should have those as well if you have the ability to have one. You should be taking a carbon monoxide reading in a home just to get a baseline of what is going on. Too much carbon monoxide in the blood can cause that person to die due to the lack of oxygen. Before dying, that person is going to feel tired and may fall asleep without knowing they are being suffocated due to the lack of oxygen. Okay, CO has also been known to be associated with Alzheimer's and attention deficit disorder. There are 2 types of fuels primarily used for gas furnaces. You're going to have natural gas and LP. Natural gas is obtained from gas deposits in the ground. It is lighter than air and consists of about 95% methane and 5% ethane or some other hydrocarbons. It has a heating value of about 1,000 BTUs per cubic foot. and 1,000 BTUs per cubic foot, somewhere's in there. To burn 1 cubic foot of natural gas, 10 cubic feet of air is actually needed. However, some excess air is needed to prevent any incomplete combustion occurring. Therefore, about 15 cubic feet of air is used for each cubic foot of natural gas, which provides necessarily approximately 50% of excess air that is needed to help support combustion. Excess air is any secondary air that exceeds the amount of air necessary for complete combustion. By designing furnaces to take a certain amount of excess air, manufacturers provide a safety buffer in case of damage or malfunction that may impede airflow and reduce the amount of air needed for combustion. Okay, furnaces with lower efficiency ratings take in between 20 and about 50% excess air to ensure complete combustion. Your higher efficiency furnaces can use as little as 10%. Excess air is also important for condensing furnaces, as it reduces the dew point of your flue gas. Dew point is the temperature at which a gas condenses into a liquid. By reducing the dew point, excess air causes the flue gas to condense at a lower temperature, ensuring that a furnace will capture the heat of condensation from the flue gas. This is the key to how a high-efficiency gas furnace works. Not only does a high-efficiency gas furnace have a primary heat exchanger, it has what's called a secondary heat exchanger. It is that secondary heat exchanger that lowers the flue gas dew point. We are actually using the heat that is escaping out to the flue and using it to heat the space. So we are also not only using the heat from the flame that is entering the primary heat exchanger, but we are also using the heat that is exiting the primary heat exchanger into the secondary heat exchanger to as well heat the space. And then by doing so, we are able to lower the flue gas temperature that is actually exiting the furnace. And as a mix of 1 cubic foot of natural gas and 15 cubic feet of air burned, it will yield about 1 cubic foot of carbon dioxide and 2 cubic feet of water. It also yields about 12 cubic feet of nitrogen and 1 cubic foot of oxygen, which are left over from the excess air used in the combustion process. So if the furnace is not designed to condense the water vapor, the flue gases get low enough that water will corrode the flue and cause the products of combustion to leak into the space. So on a high efficiency furnace, we are actually able to get our flue gas temperatures to roughly around 100 degrees. Condensation of water begins between 180 and 200 degrees. If there is not enough primary air, the flame is going to be noisy. It's going to jump around above the burner. It's not going to be steady. If the exhaust contains carbon monoxide, there is either too little or too much combustion air. LP gas consists of liquefied petroleum and butane. It is mostly propane with some butane that's out there. LP gas is heavier than air, and it can be easily liquefied under pressure, stored and transported in cylinders and tanks. When the pressure is reduced, as the LP gas leaves the tank, it vaporizes and changes into a gaseous form where it now can be burned. Propane boils at negative 44 degrees Fahrenheit at atmospheric pressure and has a heating value of roughly 2,500 BTUs per cubic foot. Butane boils at 32 degrees and has a heating value of roughly 3,200 BTUs per cubic foot. LP gas can produce more heat per pound of natural gas. It requires more oxygen as well for complete combustion. You need to understand the difference, the specific gravity of each one of these different gases in order to truly understand how it's going to burn. The heavier the gas, the more air you're going to need to support complete combustion. To burn 1 cubic foot of natural gas, or of LP gas, you need to have roughly 24 cubic feet of air in order for it to occur. About 35 cubic feet of air is needed to provide roughly 50% excess air to support combustion. Propane requires roughly 32.5 cubic feet of air for each cubic foot of gas. And then butane requires roughly 45 cubic feet of air for each cubic foot of gas that is burned. So combustion is going to change depending on what gas you are burning. Now, natural gas has a smaller specific gravity than air, so it's not going to need as much air as butane and propane would need. We would need to take that into account to make sure that we are burning all of the elements inside each one of these gases in order to achieve complete combustion.